All right, when you hear the phrase scientific method, what pops into your head? Probably a lab, right? White coats, maybe some bubbling beakers. But what if I told you that you, yes, you, use it pretty much every single day and you don't even realize it? Today, we're going to uncover the hidden scientist in you. We'll see how a really simple, everyday problem is actually the key to unlocking one of the most powerful ideas in all of human history. And to prove it, we're going to start with something that can absolutely ruin a morning: the broken toaster. It might not seem like a big scientific mystery, but believe me, the way you instinctively handle this little crisis, well, it's the scientific method in a nutshell. So picture this. You're in your kitchen, you're not fully awake yet, and you pop a slice of bread in the toaster. You push down the lever and nothing. No glow, no warmth, just a cold, dead appliance. So what do you do next? I'm betting you don't just sigh and eat cold bread. Nope, you start troubleshooting.
Without even really thinking about it, you're already going through the steps. First, you've observed the problem. No toast. Then you ask a question, what's going on here? You even come up with a hypothesis, a couple of ideas actually. Maybe it's just unplugged. And then you run your first experiment. You check the power cord. See, you're a total natural at this.
And that's it. That's the spark right there. That simple, logical little dance of observing, questioning, and then testing, it's the very same engine that's driven some of the greatest discoveries we've ever made. You're not just fixing an appliance, you are literally thinking like a scientist.
Okay, so if we're all just scientists in disguise, then what's the big deal about the formal scientific method? Well, think of it less like a rigid set of rules and more like a map. It's a guide that helps us channel all that natural curiosity into real, actual discoveries. Now, you're going to hear some fancy-sounding words like empirical investigation, but don't let that scare you off, seriously. Empirical just means it's based on evidence we can gather ourselves, with our senses. If you can see it, hear it, touch it, or measure it, it's fair game for science.
This diagram here really shows what I mean. Notice how it's a loop, not a straight line? That's so important, because in science, an answer is almost never the end of the story. Usually, it's just the beginning of a brand new, even more interesting question. We're going to keep coming back to this map as we go.
Every great scientific journey starts with just one question. But here's the thing, not all questions are created equal. The real trick is learning how to ask the right kind of question, one we can actually go out and find an answer to.
Just take a look at this comparison. A huge philosophical question like, why do plants even use nitrogen, is a fantastic starting point for our curiosity, but it's not something we can really test in a lab. So, a scientist reframes it. They turn it into something like, how does the amount of nitrogen affect how a plant grows? Now that is a question we can design an experiment around.
So here's a pro tip. If you want to think like a scientist, try starting your questions with words like how, what, or which. Those words kind of force you to zero in on something specific, something you can actually measure. It turns a giant, overwhelming mystery into a smaller, solvable puzzle. All right, once you've got a testable question, it's time for what I think is the most creative part of this whole thing, the hypothesis. And let's be clear, this is not just a random guess. It's an educated, testable prediction about what you think is going to happen. Put simply, a hypothesis is your best shot at an answer to your question, but it's a special kind of guess, right? It's one that makes a very specific prediction that you can actually go and test.
Now, to build a really solid hypothesis, you have to think about two key things: the one thing you're going to change and the one thing you're going to measure. The thing you change, we call that the independent variable. And the thing you measure, that's the dependent variable. A simple way to remember it is cause and effect.
And here is a little secret weapon for writing a perfect hypothesis every time. It's the if and then structure. If is your cause, your independent variable, and describes the experiment you're going to do. And then is your predicted effect, the dependent variable. It's just a simple, powerful way to organize your scientific thinking. Okay, that's enough theory. Let's see how this all clicks together in the real world. We're going to take our question about plants and nitrogen and actually design a simple experiment to get an answer. So, here's our official question. Does giving plants more nitrogen make them grow taller? It's simple, it's clear, and it gives us our variables right away. The amount of nitrogen is the thing we're going to change, that's our independent variable, and the height of the plant is what we'll measure, our dependent variable. Now, for our results to mean anything at all, we have to run what's called a fair test, and that is super important. It just means we only change one thing at a time. So we'll set up a few groups of plants.
Group 1 gets no nitrogen. That's our control, our baseline. The other groups get different amounts, but, and this is the key, everything else has to be exactly the same. Same light, same soil, same type of plant. That's the only way we'll know for sure that any difference we see is because of the nitrogen.
And check it out. Here are the results. This chart really tells the whole story, doesn't it? As you can clearly see, the more nitrogen we gave the plants, the taller they grew. Our hypothesis was supported by the data.
So we got our answer. Case closed, right? Well, not so fast. In science, a successful experiment is almost never the end of the road. In fact, it's usually just a signpost, pointing you toward a whole new bunch of questions.
And this is a really crucial point to understand. In science, you never actually prove anything is 100% true forever. Your results can support your hypothesis, and the more evidence you get, the more confident you become. But there's always a chance that some new discovery tomorrow could change the whole picture. So let's go back to our map. We've just completed one full loop of the cycle. We asked a question, we made a prediction, we ran a test, and we got a result. But now, that result just sparks new questions. Like, is there a point where too much nitrogen is actually a bad thing? Or do different types of plants react differently? See? The journey of discovery never really stops.
So the next time you run into a problem, whether it's a broken toaster or something way bigger, just remember that you have this incredibly powerful tool ready to go. The scientific method isn't just for labs, it's a way of thinking, a way of being curious about the world in a structured and powerful way. So I'll just leave you with this thought. What's your next experiment going to be? What question are you going to investigate?